On standard 8EEA1. This standard basically deals with scientific notation, and we're still dealing with equations and expressions. We use scientific notation to, in this case, estimate very large and very small quantities. So we're going to start with a brief lesson or brief thing out of Learn Zillion, explaining what scientific notation actually is. Scientific notation is when you have a number between 1 and 10 on the front. Look, see, 5.2 is between 1 and 10. 8 is between 1 and 10. Let's move it down just a little bit. 4.391 is between 1 and 10. You can only have one digit on the front. It can't be 0. The back is an integer power of 10. In this case, it's 10 to the third. Here we have 10 to the ninth power. Here, 10 to the negative 2. What we need to understand is whenever we've got a power that's greater than 1 or greater than 0, it's going to be a very big number. When we have a power that is less than 0, like a negative 1, a negative 2, something of that expression, it's going to be a very small number. Now, let's see what this actually is so we can understand what it is. If I have 5.2, this means we're going to move this 3 decimal places. We're going to make this 3 places bigger. We're going to move the decimal 3 places. If you've got 5.2, that means you're going to move it 3 places. 1, 2, 3. This is actually equal to 5,200. How about 8 times 10 to the ninth? Well, we need to move this 8 decimal places. You're going, but there's nothing behind the 0, behind the 8 here. We can add decimal places. There's an understood decimal there. You move it 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we are looking to, let's put in some commas. There's a comma after every 3 of them. 3, you are looking at 8 billion, right? How about this? This means we're going back 2 places. We're going to move this way 2 places, make this a smaller number. 1, and there's nothing there, so you got to put a 0 there. You now have got 0.04391, and you can put a 0 in the front. It doesn't change anything. The number this is actually equal to is 0.04391. That's how scientific notation works. You have one digit in the front, a number that's between 1 and 10. Then you've got your power of 10 back here. Now let's look at some examples of how we use this. This one says, as of March 2020, there are approximately 7.8 billion people in the world. Which of the following is the best estimate of this number expressed in scientific notation? First, let's write 7.8 billion. That's 7.8. Now we need to write that as a billion. Okay. Now let's think about billion. 1 billion. 1, 0, 0, 0. That's 1,000, correct? That's 1 million. That's 1 billion. So let's write this as 7.8 billion. 7.8, okay, or 7 billion 800 million. That's what we're looking at. Now, if we look at this, guys, this is 7.8 times 10 to the, let's see how many places we'd have to move the decimal. It's a very big number. We're going to have a number that is greater than 1 as our exponent. We move it 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.8 times 10 to the 9th. I don't see this down here. I say 7 times 10 to the 9th, and I see 8 times 10 to the 9th. What is this closer to? Remember, guys, if you're rounding something, we look at the digit behind it. If we're going to round this, whether it's 7 or 8, we look at the 8. 4 or less, let it rest. 5 or more, raise the score. So I would raise this up to being 8 times 10 to the 9th. And here's our answer right here, 8 times 10 to the 9th. Now let's do an example of a very small scientific number. The size of a plant cell is approximately 1.3 times 10 to the negative fifth meters. Look, a negative exponent. This can be very small. Which of the following could be the size of the plant cell in meters? Let's convert this to start with. 1.3 times 10 to the negative fifth. I'm going to move the decimal this direction. 1, 2, 3, 4, 5 places. I've got 4 decimals in front of that. So 0.000013. Now, I know I'm going to need 4 decimals in front of the first number. Let's see, 4 zeros in front of the first number. This has got 1, 2, 3, 4, 5. It's not this one. This one's got 1, 2, 3. It's not that one. 1, 2, 3, 4. It could be this one. Let's look at this one. 1, 2, 3, 4, 5. Nope. 1, 2, 3. Not this one. 1, 2, 3, 4. Could be this one. So let's look at this 13, 1.3. Is that closer to 1.275 or 1.38? Well, if I look at this, if I were to put the decimal there, 1.275 would round to 1.3. 1.38 would round to 1.4. So this is what we're looking at right here, this C. C is the one we're looking for. Now let's try this. Use scientific notation to compare how many times as much one quantity is to another. How many times means to set up a ratio. Anytime you see it, it says how many times we set up a ratio. This says Hannah has 6.6 times 10 to the 5th rocks in her collection. Derek has 2.2 times 10 to the 3rd rocks in his collection. How many times more rocks does Hannah have than Derek? They ask about Hannah first. Hannah has more rocks. We would put her on the top, 6.6 times 10 to the 5th. We would put Derek on the bottom, that's who we're comparing to, 2.2 times 10 to the 3rd. When we do this, guys, when we're dividing like this, we separate these into units. 6.6 divided by 2.2. See, I've got the numbers over each other. Now let's put the bases with their exponents over each other. That's times, not equals. 10 to the 5th times 10 to the 3rd. Let's divide 6.6 by 2.2. And if I do that, I'd move my decimal. 22 goes into 66 3 times. So I'm going to substitute 3 in place of this 6.6 divided by 2.2. When I'm dividing and I have the same base, like bases, I subtract the exponents. This would give me times 10 to the 5 minus 3. Now I've got 3 times 10 to the 2nd power. 3 times 10 to the 2nd power, let's move the decimal on that one. 2 to the 2nd power means I would move this 2 places. That means that Hannah has 300 times. Hannah has 300 times more rocks than Derek.